colleagues. Am I being heard? Everything works fine. Good. It is a great pleasure for me to give a talk here, and the topic of my presentation is a lighting assembly based on red and blue light-emitting diodes as a lighting source for space agriculture. Light-emitting diodes, or LEDs, have been considered as a lighting source for space agriculture for quite a long time. Due to their technical characteristics, they are a very promising lighting source for space applications. In the numerous works concerned with the design of such lighting sources, it was found that a lighting source based on red LEDs with a small addition of blue ones allows most crops to yield sufficient biomass. However, not all crops reacted equally well to such lighting, and the more subtle physiological effects of such lighting on plants are poorly understood. Also, most of the previous work was done with rather low irradiances. Producing high biomass in agriculture would require higher irradiances, which modern light-emitting diodes can provide. So the aim of our works was to see how green crops would grow with a red and blue LED lighting source at higher photosynthetic photon flux densities, about 400 micromoles per square meter per second. In our experiments, we used Chinese cabbage, the cultivar Vesnyanka. It is a green crop, in many ways similar to lettuce. We wanted firstly to repeat the previous works with smaller irradiance, about 100 micromoles per square meter per second, and do a thorough study of the photosynthetic apparatus of these plants and their growth and development. And finally, we wanted to test how these plants would grow and photosynthesize at higher ppfs, about 400 micromoles per square meter per second. In plants grown with, we used two lighting sources for our experiments. The LED lighting source was composed of red and blue LEDs with maximum emission spectra of 650 nanometers and 470 nanometers respectively. The ratio of red to blue photons was about 7:1. As a control, we used a high-pressure sodium lamp. In this slide, you can see the spectra of the lighting sources we used. The HPS lamp emits most of the quanta in the yellow-orange range, and the LED lighting source has two narrow emission bands in the blue and red range. Plants grown with 100 micromoles ppf had a shoot fresh weight, which in this crop equals to edible biomass, only slightly lower than the control plants grown with a high-pressure sodium lamp. However, the dry weight of the shoots was lower than in control plants, while the dry matter content in the shoots was also slightly lower. Plants grown under LEDs with 100 micromoles per square meter per second ppf had significantly lower sugar content in the shoots. We did not see any significant differences between control plants and LED plants in photosynthetic pigment content and the work of the light reactions of photosynthesis. However, their photophosphorylation activity was unusually high. Photophosphorylation is one of the key reactions that lets the plant transform light energy into the energy of chemical bonds. So these plants had a very high capacity of producing energy from light. However, it did not result in high biomass production or high sugar content. We also found some differences in the development of LED plants. The shoot-to-root dry weight ratio didn't differ significantly from control plants, which indicates a more or less even organ development. However, plants grown under LEDs had a significantly longer life cycle, It was up to 175 days. Control plants had a life cycle of 120 days. Thus, in plants grown under an LED lighting source with 100 micromoles per square meter per second, we found relatively normal edible biomass accumulation, but they accumulated less dry mass and less sugar. We also found some changes in the functioning of their photosynthetic apparatus and changes in their development. Thus, we concluded that a lighting source based on red and blue LEDs is insufficient for this culture. We found even more differences in the growth of our plants when grown with a higher ppf of 400 micromoles per square meter per second. They accumulated less shoot fresh weight. Shoot dry weight was nearly equal to control plants, but the shoot dry matter content was about 2% higher than in control plants. In this cultivar, this indicates a loss of taste quality. As in plants grown with a lower ppf, plants grown with 400 micromoles per square meter per second had lower sugar content in shoots. Their photophosphorylation activity was also lower than in control plants, which indicates an impairment of photosynthetic processes. Plants grown under LEDs with 100 micromoles per square meter per second had a significantly higher shoot-to-dry weight ratio than control plants. It indicates an imbalance in organ development. The length of the life cycle of plants grown under HPS lamps and LEDs was relatively equal with this irradiance. However, plants grown under HPS lamps by the end of their life cycle have flowered and produced up to 25 inflorescences per plant. In plants grown under LEDs, we did not observe any flowering. In this slide, you can see the pictures of our plants nearing the end of their life cycle. You can see the flowers and even some fruit on the plants grown under HPS lamps. Plants grown under LEDs do not flower. Thus, in plants grown under LEDs with 400 micromoles per square meter per second, we found a lowered edible biomass accumulation, lower taste quality, changes in the photosynthetic apparatus and its functioning, and more pronounced changes in plant development. We conclude that the metabolic and developmental changes, which occur already at low irradiances but are not that obvious, become even more pronounced if you grow plants with higher irradiances. Thus, from this study, we can see that the narrowband lighting emitted by LITD diodes can affect plant physiology in subtle ways, which are hard to predict from the position of physiology. We believe that in the future, a physiological approach might be promising in designing lighting sources based on LEDs for space greenhouses. If we can uncover these subtle changes that occur in plants with the influence of narrowband lighting, we can try to control plant physiology and design specific lighting sources for different cultivars, different photosynthetic photoflux densities, and different applications. For example, if we need a high biomass yield, or if we need the plants to flower or perform some experiments, we might need lighting sources with spectra that would be different. In this regard, we are planning to test lighting sources with other emission spectra in regard to our cultivar. And now I would like to present some preliminary data of the first couple of experiments. We use high-pressure sodium lamp as a control and a number of lighting assemblies based on warm white LEDs. One of them is just white LEDs, Another one is warm white LEDs with a supplement of red LEDs. And another one is warm white LEDs supplemented with red and blue ones. The photosynthetic photon flux density we have is about 370 micromoles per square meter per second. The preliminary data suggest that we can await the best results from the lighting sources with white LEDs supplemented with red and blue diodes. Warm white LEDs alone may provide not such a good result. And here are some pictures of our plants grown under HPS lamps, warm white LEDs alone, white LEDs plus red ones, and white ones plus red plus blue ones. As we can see, all the plants look relatively healthy, and I think there is promise in such lighting sources. In the end, I would like to thank our colleagues at the All Russia Research Institute for Vegetable Crop Breeding and Seed Growing for providing us with plant material for our experiments, the Center for Light-Emitting Diodes and Optoelectronic Technology of the National Academy of Sciences in Belarus for providing us with the LED lighting sources. I would like to thank my colleagues for their cooperation and their support, and I thank all of you for your attention. If you have any questions, please feel free to ask them.